Thank you. Right, yes, I'm Ben. I'm one of Dirk's postgraduate students, and thank you for coming tonight for the talk on the history of exoplanet observation. Before we get into the main talk, I just wanted to tell you a bit about my research. I'm part of a bigger project that we're doing to investigate the conditions of the formation of terrestrial planets. So that would be mainly planets that are formed in the inner disk area. This is a picture, it's a bit cut off at the bottom, but this was one of the earliest, one of the youngest YSOs ever directly observed about 4 years ago. And a YSO is a big ball of gas that's not quite a star yet, so it's what's going to become a star. And this is where the planets begin to form in these rings here. Well, the gaps is where they form. And our project is mainly concerned with the conditions for the formation of the terrestrial planets in the inner disk. My part of the project is to try and cluster these objects in some meaningful way to test simulations of a disk model, so that a disk model will generate a light curve. And the idea is to then cluster these light curves, so each dot represents a separate YSO, and if you put in an artificial one, the idea is that it will end up within the main group and not out there in those outliers, and then we can say, well, the simulation is either correct or not correct. But we can't actually say it's completely correct, but we can say it's definitely not wrong, if you can understand that. So that's my part of the project. So what is a light curve? This is a real light curve from an object that's observed, and this is an artificial one. Now, to test the method of clustering, we wanted to make a light curve that's as unrealistic as possible, because YSOs, they never take this form. There are some stars that do, but YSOs don't. So this is what we decided to put into the algorithm. And I'll just go back. Clustering algorithms, they don't actually. You can't put these light curves directly into them. So what we have to do is summarize the statistics somehow of these of the variability. So that's what we do, and we create these fingerprints. Now, one of these is the real one, and one of these is the artificial one. Would anyone like to guess which one is which? Not Dirk, obviously. James?
The one on the left?
Is the...
Real?
No. No, that's the real one, actually. The artificial one, it would be completely symmetrical, but we've used a real cadence, so it doesn't come out. Now, what these are is that each pixel represents a probability that the star varies by a certain amount. And the reason we have to put the light curves into this format is because the clustering algorithms, first you have to reduce the dimensions as much as possible, and by that I mean each point on a light curve is a dimension. So if we reduce them down to these images, we reduce them from thousands down to a couple of hundred. And also the number of dimensions in each image has to be exactly the same for every image. And this is basically two clustering algorithms that we've put these images into. This is a rather complicated algorithm that uses machine learning. And this is a k-means algorithm, which just kind of reduces it down to two dimensions and then plots those dimensions on a space that you can visualize. This object is basically an object that a file that has no data. That's why it's ended up there, which was quite a good result because it sort of gave us a clue that this would identify objects that are not like the main group, like here. So to test it, we put in 3 different sine curves. And that was the outcome. Sorry. Now this one you can see it's basically destroyed all the clustering, so that's bad. And the 3 artificial objects are nowhere near each other, so they've gone off and been plotted in separate areas. So that's also not good because 3 sine curves should really end up next to each other. And it's and on this one, those are the 3 artificial ones, and this is the main group. So that's good for 2 reasons. First, it means I can publish a paper and get a master's. And second, Dirk's already put in a grant application for the rest of the work, so it means he might actually get the money. So that was that. I'll try not to bore you anymore with my own research and on to the main thrust of the talk. So exoplanets. This was the first one ever discovered around the pulsar. The imaginatively named PSR B1257 plus 12b. Thanks to Holly for the sense of humour. It's not quite done like that. There is a method to the madness of these numbers. This is actually the right ascension and declination of the object, and PSR obviously stands for pulsar. And the letter is the planet of if there's more than one planet, it'll be B, C, D. So they're in the order that they're discovered, not the order they are in the system. And for some reason they start at B. I don't know why they start at B. There must be a reason for that, but they do. This was discovered in 1992, and it was the first exoplanet discovered. And it was discovered by sorry, my mind's gone blank. By timing variation. Pulsars emit a very steady but quick burst of radiation from themselves to the observer, and these are very, very steady beams of radiation which you can observe. And as the planet moves round the star, it wobbles the star slightly, so these signals get slightly closer and further apart depending on where the planet is and which direction it's moving, and causing the star to wobble. So this graph here just shows you the variation in the velocity of the signal that's coming in. It sounds simple, but the trick is in the accuracy. These signals are extremely close together. So they vary by only sort of 2 nanoseconds, well, less than that actually. 0.03 nanoseconds over a period of, say, 2 months maybe. So that's very, very small perturbations in the signal. This was the first exoplanet discovered around a star like ours. This is PEG 51 PEG B. it's a hot Jupiter. It's very close to its star and orbits very fast. I think its period is something like 3 days. I'm not sure on that. This animation glitches slightly. So this is what happens if you observe a star without a planet. The light comes towards you, and the spectrum, I don't know if anyone was at Yv's talk, but you can see that the spectrum of light remains constant. These lines do not move because the light is constant and there's no velocity change in the star. And what happens when a planet orbits it is it just changes the motion of the star slightly. So as it goes away, the light becomes more red, and as the star comes back towards you, it becomes slightly more blue, so that you can detect a velocity change. And these lines here, again, it moves as the star moves, but it looks like it's actually moving quite a bit, and that's for an example, but in reality it doesn't move anywhere near that much. In fact, it doesn't even move it's like 1% of a fraction of the line that it actually moves. So the trick is again in the accuracy. This is the RV graph from the actual observation. Now, the idea for this was proposed in 1952 by Otto Struve, but at the time, the accuracy of spectrographs that could measure this change in the frequency of light, the accuracy was in the order of about 1,000 meters per second. And no one really thought, it's possible that we can do this. But also, they didn't realize that hot Jupiters could appear that close to their sun. If Jupiter was where our planet Jupiter is, if that hot Jupiter was as far out as ours, firstly the star would only move in the order of sort of 12 meters per second, and also Jupiter's period is 12 years. So to observe it 3 times, you've got to wait 36 years, which is very, very, very difficult to do. But Peg B, obviously, because it's closer in, it has a much bigger effect on the star, and it moved sort of about 75 meters per second, maybe a bit more. So that was something that was unexpected, and we certainly had the technology to do this in the 70s, but because we didn't realise that hot Jupiters could appear in that part of a star system, we never really looked, or no one really thought to look, and it didn't happen until 1992. 5 actually, I think it was this one. So this was the first planet discovered. Well, not discovered. It was discovered by radial velocity method, but this was the first planet that was observed using the transit method. Now, the transit method works by the planet moving in front of the star and dipping the light. So if you remember back to those light curves, if a planet moves in front of the star, they would dip. The signal would dip. That you get the points. The point, one point would be there, then down a bit, and then down a bit. But the thing is, stars are very big, and planets, although they're big, they're not anywhere near as big as a star. So they would only cause about 1% dip in the light. Now this was possible as soon as basically we had CCDs. So in 1999, this is the original data from how this planet was discovered or confirmed using the transit method. And this was taken with just a camera, I believe, so not even a telescope. And then later on, this was an observation done by Hubble, and you can see the difference in signal, but you can also see the percentage of light that moves, that the star dims by is very tiny, 1.5%, 1.6 maybe. So it's very difficult, but very possible with a CCD. And as soon as those were invented, then obviously the transit method was much more viable. The reason these are more spread out on the second set of observations is because they used a shorter exposure time on the camera for that set. And I've just got a little animation that describes the transit method probably much better than I can explain it. So we've got the planet coming around the star, and then that's the light emitted there, and you just see a little dip as it passes through. So the size and length of transit gives information about the size and orbit of a planet. But what about if there's multiple planets? You're going to get mixed signals. So what you have to do is just, again, you measure the light that comes from the star. Another animation. And you can pick out the planets by their transit dips. So you've got the biggest planet there, and then you've got the next two, and then it dips again as the second, and then goes back up, and then that's it. So I just watched that again. So it's quite good. So you have to then pull out this information from how many planets are in the system just from their light curves there. And also, the transit method has other benefits. You can gain a lot of information about the atmospheres of planets, and because of something called absorption spectroscopy. Now, when light passes through a gas, certain atoms and molecules will absorb different parts of the light, different energies. And you can see from these peaks here, they give like a signal that you can read, and by that signal you can then tell what exactly is in the atmosphere. Now that's the same planet, HD 209458, and this was the first time that an atmosphere had been analysed by this method, and they detected sodium in the atmosphere, very sodium rich. So the transit method, Kepler has been outstandingly successful. It's a finished mission now, but the transit method added more planets to the database than any other method. There's also another way of detecting exoplanets is direct imaging. This was the first exoplanet discovered by direct imaging in 2005. It works best in the infrared, but it requires very high precise instruments. Now this star is actually a brown dwarf. So this image has been, as the planet moves around the star, there's a a change in the frequency of light that's reflected from the star, and it's then that's subtracted from the spectrum, and you can literally remove. Basically, what's happened is they've removed as much light as possible, and then you can see the star and the planet. So they've basically blocked out the light from the star. So even though that's a brown dwarf, it looks white, but that's not the actual colour of the star. It's a very, very dim star. This is not possible with very bright stars. And the reason that's red and this is white is basically because even though the light's blocked out from the star, it's still much hotter than the planet in terms of emission. The last method I wanted to show you was gravitational microlensing. Now this is slightly more complicated. Basically, as a star that's behind the star and planet as it moves across, the gravity well from the star and the planet magnifies the light from the star behind. I'll just play that again. Now, because of special relativity, stars and planets, they warp space slightly, so it has a magnifying effect of the light behind. And what happens is the star and the planet, as they pass through, they have their own signal. Now, this is only possible in certain circumstances. Firstly, the star and the planet have to pass directly in front of another star in terms of the line of sight. And also, it's unrepeatable, which means that you can't really confirm it once you've detected it. So it's only really good for providing a candidate for other methods to then be applied to it to confirm the discovery. I've got some actual data which would explain it slightly better. Now, it doesn't need a large telescope. That's one good thing. This is the discovery of the first one, and you can see the signal from the star. So what would happen is the star would be moving across in front of the light, and the planet's next to it, and they both have their own signal. So this is a magnification of the star's light as it passes in front of another star, and this is the magnification of the planet's light down there. So if the planet is too close to the star, it doesn't work because they become merged, and also they have to pass by at the same time. So it only works in certain ranges. Only out to about 4 AU out is about the best range. But you do not need a large telescope. So these are the sizes of 3 of the telescopes that we used, which is actually quite a decently small size of telescope. So how many so far? This was accurate up to about 8 or 9 days ago, and it's probably not accurate now. We're finding it at such a terrific rate that it's all constantly updating. But as you can see, the transit method is by far the most successful method, and then radial velocity. Poor old astrometry, 3 planets discovered so far, and I think they're about a decade apart. I've actually got a bar chart which, yeah, they are. They're about a decade apart. But that will change. Now, what this graph shows in terms of when they were discovered and their quantities is is kind of the individual missions as well. You can see Kepler here, data release 1, data release 2. And these numbers are quite small, but this one, I believe that was TESS, I'm not sure. Yeah, I think that was TESS. Let's have a look. Yeah, these are the missions. Now, Gaia is a mission that's ongoing, and it's a mission to basically track about 1.8 billion objects in the sky, but track their movements. So the astrometry will probably go from 3 to, well, quite a lot. K2 is actually Kepler's extension, but that's finished now, 2018. But there's more missions planned. I don't really know the details of those, but I'll make the slides available, so if anyone wants to look them up, I'm sure they're very interesting. Yeah, so Gaia will undoubtedly add hundreds, if not thousands, of new exoplanets to the database. It maps, yeah, their motions, their luminosity as well. Now, why would I say that? It's quite a strange slide. Wood is more valuable than diamond. Would anyone like to guess why?
Because with wood you can make materials and actually use it. Well, diamond, it is strong, but it's very difficult to mine and it's extremely expensive. And
Yeah, good answer. The thing that I was thinking of was that we've only found wood on one planet so far, which is ours. This is 55 Cancri. It's not a very nice place to live, admittedly. It's very hot, about 2,000 Kelvin. But much of its interior could be made of carbon, up to a third of which could be diamond. It's tidally locked with its star. It's basically a super Earth that's very close to its star. It's about 8 times the size of Earth, so that's a lot of diamond if it is true. There is some evidence that it is. This is a density model and puts 55 Cancri right in the carbon range, and also here as well. This is some chemical analysis. Now the reason they think it's probably carbon is because they've detected a lot of carbon in its atmosphere, and because it's very close to its star, it should in theory have its atmosphere blown away and not have an atmosphere. But the fact that there is quite a bit of carbon in its atmosphere means that it's being replenished from the planet itself. So yeah, it's quite strong evidence really that it's made of carbon, and the size of it and the pressure in its interior would definitely mean that it's got quite a bit of diamond in it. Future discoveries. Now this is another large planet. Its temperature is about 265 Kelvin. That's about -8 degrees centigrade or Celsius. It's got a hydrogen-rich envelope, and it was discovered by Kepler again. Now, the gravity is about 12 meters per second squared. Earth's gravity, for reference, is about 10 meters per second squared. 9.81 actually, but about 10. So it's uncomfortable, but it's you could walk around on it. Now, if anyone understands these graphs, perhaps you could explain them to me. I'm available afterwards. But basically what they're saying is there's three possibilities for that planet. It could either be a lifeless Hycean, an inhabited Hycean, or a mini Neptune. Now, if anyone recognises these molecules, basically they're signatures for life. The conclusions of the paper basically ruled out this option. So there's a 50-50 chance it's either a large rocky planet, possibly with life on, or it's a mini Neptune. So this is quite an exciting discovery. I think it's a guy from Cambridge that's doing the research on this, and it's been in the news lately, and it's kind of the best possibility we've got of finding life outside our own solar system. Personally, I think it would be better to look inside the solar system, but this is quite a good discovery that's come out recently. And another recent paper is something called on the Brocken spectre. It's called the Glory effect. Basically what it is in the atmosphere, if you get spherical droplets, they produce this effect. Now this is the Glory effect on Earth, and this is a simulated Glory effect of what it would look like on planet Venus. Now, different atmospheres obviously give different signatures. This planet WASP 76b, they think they've detected the Glory effect on it. So, what happens is as the planet goes around the sun, this is a light curve, but it's a secondary light curve. So it's basically, this is as the planet gets close to the sun, the amount of light that we receive from it is at its maximum, and then as the planet goes behind it, it dips down. And if you notice, they're slightly different on each side of as the planet re-emerges again from the other side of the star. They're slightly different magnitudes, which could imply the Glory effect. Now, why is this important? Well, firstly, it's the first time we've observed this effect on a planet outside of the solar system. But also, it can give new information about the atmosphere, because the Glory effect requires spherical objects in the atmosphere. So it means that not only can we tell what's there, we can tell that the atmosphere is consistent and stable over a long period of time. It does also mean it's got clouds, so very much like England. Yes. So thank you for listening. If anyone has any questions, I'll be glad to try and answer them.